In this PowerPoint, we will take all the gas laws we have learned and combine them into a combined gas law so we can deal with all the different properties of gases in one combined law. And then we'll talk about the ideal gas law, okay? And so which means that you remove all the proportionalities and then introduce a constant. So we'll talk about the ideal gas law. And then lastly, we will talk about the applications of gas law. What do you use them for, okay? And so that's what's covered in this PowerPoint. So now finally we have to combine all the gas laws, all right? And combining the gas law is the relationship between the volume, the temperature, and the pressure, all right? And so PV over T is equal to constant, okay? And remember, P and V, pressure and volume, are inversely proportional to each other, which is why they're on the same side. Volume and temperature are directly proportional to each other, okay, and that's why they are on top of each other, numerator and denominator. So an initial set of values of pressure, volume, and temperature is going to be equal to a final set of volume, because the pressure, volume divided by temperature is equal to a constant. This is how you will find the equation in a lot of books. I like to also include Avogadro's law in this, okay, because in this equation you don't see Avogadro's law. So I like to include the Avogadro's law in this. And so then my equation becomes P initial, V initial divided by N initial and T initial. So initial set of values for pressure, volume, moles, and temperature is going to be equal to the final set of values. I also use P1, V1 is equal to P2, V2. I'm used to the numbers. If you like initials and finals, you can use initials and finals. If you like ones and twos, you can use ones and twos, and that's fine. Either way, the important thing is that you need to make sure that your set of values stay on the same side. Okay, so your initial values stay on the same side and your final values stay on the same side. The nice thing about the combined gas law is that not only do you get to see the relationship that you have learned about. So for example, not only do you see the Boyle's law here, which is P is inversely proportional to V, and you also see the Charles law, which is V and T are directly related, and then V and N are directly related. So you see those laws here, but you also see the relationship between pressure and temperature. You see the relationship between pressure and moles. So for example, if you increase the number of moles, then the pressure should increase. Why? Because they're numerator and denominator, which means that they have a direct relationship with each other. Okay, and so the same thing with pressure and temperature. If you increase the temperature, pressure will also increase, because again they are numerator and denominator, so which means there is a direct relationship. Okay, so I like the combined gas law with all the laws in it so I can see all the relationships. Okay, so conceptually it becomes easy for me to understand my problem. So here is a problem that you can solve with the combined gas law. All right, so here are divers working in the North Sea platform experiencing the pressure of 5.0 times 10 to the power of 1, which really is 50 atmosphere, at a depth of 5.0 times 10 to the power of 2 meters. If a balloon is inflated to a volume of 5 liters, the volume of a lung at that depth, which depth? The 5.0 times 10 to the power 2, at a water temperature of 4 degrees Celsius, what would the volume of the balloon be on the surface? Okay, and there the pressure is 1 and the temperature is 11. The first thing we have to do is we want to make sure that we set our numbers straight, okay, which means that we have our initial set of values and our final set of values. So our initial is 5 liters at the pressure of 5.0 times 10 to the power of 1 atmosphere, and at that pressure and volume, the temperature was 4 degrees centigrade, which we immediately convert to Kelvin. So we don't have to think about this anymore. And then we get our final set of values. What would the volume be on the surface at pressure 1 atmosphere, which means the final pressure is 1 atmosphere and the final temperature is 11. And again, I convert my 11 immediately to Kelvin. All right, so now I have my initial values all set up and my final all set up. Then I go ahead and find my formula that I need. Again, remember, cross multiplication is your friend and use that as much as possible. So here is P1, V1, T1, okay? And T was down here, so it came up, and P was up there, it came down, okay? Cross multiplications. So this is really what you're trying to do here. The nice thing about setting up a formula like this is that once you have your initial and finals numbers all set up, and once you have your formula set up, then all you have to do is plug in all the numbers. All right, so it makes life a lot easier. So if you're not comfortable with cross multiplication, please learn it a little bit, take some time and do the cross multiplication. Once you get your calculator and you do the calculation, you should get 2.6, 10% to the power of 2 liters. Now, let's look at this answer, okay, and see if it is justified and see if we can justify this. So if you're working at a lower pressure, okay, at a higher pressure of 50 atmosphere at a lower temperature, if you come to a higher temperature and lower pressure, the volume should increase. First of all, your temperature is increasing from 4 to 11. So if that is increasing, then the volume should increase. The volume, the pressure is also the pressure is decreasing. So if the pressure is decreasing, the volume should increase, which it did then. Okay, so it went from 5.0 liters to 2.6 times 10 to the power of 2, which is 260 liters. Okay, that's quite a big change. So that's how you solve a problem if you have a combined gas law. Now we look at what is called the ideal gas law. When you think about an ideal gas law, think of the word ideal. It means that something that is predictable. This is how it should be. So in case of ideal gas law, we try to predict the behavior of gas under certain set of conditions. So under those set of conditions, you need to look at all the conditions, which means you need to look at all the laws that we have studied so far and try to come up with one law, okay, that will help us with all the different things that we can change, okay, which means all the variables. One of the common variables in all the laws was volume, okay. So in case of Boyle's law, volume was inversely proportional to pressure. In case of Charles, it was directly proportional to temperature. In case of Avogadro's, it was directly proportional to number of moles. So when we combine all of these things to give one law, it means that the volume is directly proportional to moles and temperature and inversely proportional to pressure. Okay, so now we have this one beautiful looking equation, which now if we want to remove the proportionality symbol over here, we need to add a constant, okay, as we've been talking about. So adding the proportionality constant, okay, will give us this kind of an equation. So now we're not looking at an initial set of values or final set of values. We are going to just go ahead and remove the proportionality symbol, but then you have to add a constant, okay, which is given by R, and R is what we call the gas constant, okay. And so we rearrange this equation now to give something which is a little bit easy to remember, and that is called PV is equal to nRT, okay, where you try not to have any denominators and put everything in one line, okay. So PV is equal to nRT, pressure and volume is equal to N is the number of moles, R gas constant, and T is temperature. So now R actually has to have a number, okay, to it. We just can't let go, okay, of R. And so the way we get the number is this, okay. This is a chart that's given in your textbook also, not exactly the same one, but similar. And in that case you will find, and in that chart you will find that we have all the values of R. Now why do we have so many values of R? And that has to do with the kind of units you're using. So if you look on the first one, we have 0.082058 liters atmosphere divided by Kelvin mole. All right, and so if you look at the gas constant, okay, in case of gas constant is PV over NT. So which means PV over NT. Okay, and so that's how you get these units. So once you look at the units also of any constant, you can figure out the formula, okay, of that particular law, okay, or any kind of an equation. As we go down through all these numbers, you will see that the units are changing, all right, and the units change according to what type of equation you're using, because not all pressure is going to be in atmosphere. In some cases, the pressure is going to be in weight and meter square. All right. In some cases, the pressure is going to be in pascals. So in those cases, the numbers are going to be different. All right. And so you choose a number according to what equation you're working with. For us, our constant is going to be 0.082058, which we can round off to 0.0821 liters atmosphere per Kelvin mole. So this is going to be our constant from now onwards, which also means that you need to make sure that every time that you work with an equation or with a problem, that you convert all your units to liters and atmospheres and kelvins and moles. Okay, so if your units are not consistent with these ones, then of course you will get a wrong answer. Standard temperature and pressure is a condition that we kind of need to understand, because this is how we can predict how a gas is going to behave. So we need to have some sort of a standard where we can say, okay, you know, I know a gas is going to behave like this at this particular temperature. Okay, and so for that particular temperature, that is 0 degrees Celsius. Okay, and that particular pressure is 1 atmosphere. All right, now 1 atmospheric pressure is a very common pressure. Okay, almost everybody feels about 1 atmosphere of pressure. 0 degrees Celsius, of course, is very cold. Okay, that's the freezing point of water. And so that's a little bit cold. So that's not really quite standard as far as normal day-to-day conditions are concerned, but that's not the point. Okay, the point is to have a certain set of numbers which you can call standard and say, okay, all gases at STP behave like this. Okay, and this gas at STP behaves like this. So you need to have a certain set of numbers. So then the 0 degrees Celsius and 1 atmosphere are the standard temperature and pressure. Okay, but then what about the quantity of gas? Okay, how much is that going to be? So the quantity of gas then is 1 mole. All right, and in those conditions of that temperature and that pressure and that quantity, the volume of the gas occupied is 22.41 liters. All right, so these are the STP conditions, by the way. So make sure you convert the Celsius into Kelvin. Okay, and then of course we have all of these numbers. By the way, this is kind of how we also calculate for R, in case you're wondering where we got this magical gas constant from. The gas constant comes from looking at all of these conditions and then measuring the volume and the temperature and pressure at a certain amount of gas, and then trying to figure out what the gas constant is going to be. Okay, and the gas constant should come out to be the same if you have these set of conditions. Okay, so let's look at a solved problem now for gases. So let's read the problem. A steel cylinder with a volume of 68.0 liters contains oxygen at a pressure of 15,900 kilopascals at 23 degrees Celsius. What is the volume of this gas at STP? So this problem really is about initial and finals. Okay, the initial numbers are given to us, which is 68 for volume, and the pressure is this much in pascals, and then the temperature is given, and we are asked to calculate the volume at STP. So we know the STP conditions already, which is that pressure is 1 atmosphere and temperature is 273. Now remember, the volume can change, okay, depending on how much moles you have, which we're not given the moles of, so we can't really outright say how much volume we have until we calculate it. So these are our STP conditions, and because these are one set of values, we need to make sure that the other set of values are in the same units. Okay, so first thing we do is convert the units, all right, and make sure they're both the same. And it's best to convert everything into the standard units for gases, okay, which is atmosphere and Kelvin and liters. So pressure, convert that from kilopascals to atmosphere, and that's what you get, 157. Temperature, convert that into Kelvin. All right, and since this is an initial and final set problem, you need to get the combined gas law. And since we are using P1V1, I thought we'll go ahead and use this as an example instead of initial and final, because it's essentially the same thing anyway, but it'll give you an example of how to use this kind of an equation. All right, so now we're calculating for V2. Remember, N is not given to us. We don't have the number of moles, which means that we don't really need to have N over here. It also means that it might be constant, okay? So we don't have to worry about N over here at all. So which means P1V1 over T1 is equal to P2V2 over T2. We are trying to find out the volume, so which means that during cross multiplication then P1V1 times T2 should be divided by the T1 and then P2, okay, which is what we have over here then. Plug in all the numbers according to what you filled out, okay, over here, and here is your final volume, okay, that you will get at STP. So this is how you would solve this kind of a problem. Here is another one, and let's read the problem. A 50.0 liter cylinder of nitrogen gas has a pressure of 17.1 atmosphere at 23 degrees Celsius. What is the mass of nitrogen in the cylinder? So this question is not about initial and final, it's actually about the ideal gas law, all right? PV is equal to nRT. So that's what we're going to use in here. Now, in this case, we are asked for the mass of nitrogen, which means that we need to figure out the number of moles that we have. Once we know what moles we have, we can convert that into grams, okay, of nitrogen. So first of all, we need to make sure that we have the right units, and we have the right units for the volume, we have the right units for the pressure, temperature, we convert that into Kelvin. So once we have all the right units, then we go ahead and rearrange our equation to give us for moles. So PV over RT will give us the number of moles. Plug in all the numbers in here. Make sure you have all your units so that way you can cross them out as we go across. So atmosphere, atmosphere, liters and liters, and Kelvin and Kelvin. Okay, everything crosses out. And then you're left with moles, okay, which inverse of inverse is really on the top, all right? So number of moles comes out to be 35.20 moles, which then you can find the grams of by using formula mass, okay, from the periodic table. So N2 is 14 times 2, which is about 28 grams, all right? And so then you find the mass. So this is how you would use the ideal gas equation. For an ideal gas, calculate the pressure of the gas if 0.215 moles occupies 338 milliliters at 32 degrees Celsius. Okay, so that's the problem. So we find all the different things that we have, which means the number of moles is given to us. Volume is given to us in milliliters, so you convert that into liters. Temperature is given to us in degrees Celsius, so you convert that into Kelvin. Okay, then we're getting almost there because we're supposed to calculate the pressure. Okay, and just remember PV is equal to nRT, and therefore pressure is equal to nRT over V. Okay, and so you plug in all your numbers in. Again, use all the units. Okay, use all the units, that way you can cross them out and make sure that you have the right thing. Okay, in there, Kelvin, Kelvin crosses out, and you're left with atmosphere. Okay, in there. And so then here's your final answer. Make sure you bring things down to the correct significant figures when you're doing all of these things. Do not round off in the middle anywhere. Okay, so wait for the final answer and then you round off. So again, this was an ideal gas equation problem. Really very easy problems to do once you know how to get to the right units. One of the applications of gas laws is to figure out the density of a gas, or to calculate the molar mass, okay, of a gas if the density is known. So the way to do this is to rearrange the gas law, okay, a little bit. And so you get started by putting the number of moles and volume on one side, and then the pressure and temperature and gas constant on the right hand side. Okay, remember, you're not changing the ideal gas law, you're just rearranging it. Okay, remember PV is equal to nRT. So you got your number of moles and volume on one side. Then you multiply both the sides by molar mass. Okay, and remember, molar mass is grams per mole, which is coming from the periodic table. Okay, that's what we know so far. And so here, looking at just this part over here, not on the right hand side, just the left hand side, this is grams per mole. So grams per mole, the moles will get cancelled out. So you're left with then grams per volume. Grams per volume is density. Okay, and so your final equation is density is equal to pressure times the molar mass of the gas divided by gas constant and temperature. You have to remember that the units of density here are grams per liter and not grams per milliliter as we did in chapter 1. Okay, so this is liters, you're not changing those units. To find the molar mass, you can rearrange this equation and solve for the molar mass. Okay, so now dRT over P will give you the molar mass of the gas. All right, so if you have an unknown gas that you need to figure out, then you just calculate the density of that gas and then put it in the gas equation, and the mass that you will come up with is going to be the molar mass, and you can look up the periodic table and identify the gas. So here is a problem. What is the density of methane gas, CH4, at 125 degrees Celsius and 3.5 atmospheres? Okay, and so let's go ahead and plug in all our numbers that we need. The molar mass of methane is CH4. So 1 carbon plus 4 hydrogen will give us that many grams per moles. Pressure is 3.5. The temperature that's given to us is 125, and so the Kelvin is 398. This C does not belong with the equal. The C belongs right here, actually. Sorry about the little problem there. Density is equal to molar mass times pressure divided by the R, which is gas constant, and then the temperature. Okay, very easy to do. All you have to do is plug in all the right numbers in the right place, and you should come up with the right answer. And again, note the units here. They are grams per liters and not grams per milliliters. All right, so leave the units as they are. Cross out the units that you don't need. Okay, so grams, there's nothing to cross out grams with. Moles is gone, atmosphere is gone, Kelvin is gone. And so you're left with grams and then liters, okay, over here. So that is a nice example for calculating for density. Simple problem. Here is a list of what you've done so far with all the gas laws. And so it's not quite the applications, but really in a way, these are what the gas laws, okay, are, which is that the gases are compressible, okay, and that is because gas molecules are far away from each other and they're separated by large distances. The magnitude of pressure will depend on how much and with how much force the molecules of the gases will strike the container walls. Okay, and then of course we had the 4 laws that we talked about. The Boyle's law, which is a relationship between pressure and volume. Charles' law, which is the relationship between volume and temperature. And then Avogadro's law, which is the relationship between volume and number of moles. And then finally, we just did Dalton's law, which is that each of the gas molecules in a mixture will exert their own pressure. So as you saw, we learned about the combined gas law. We learned about the ideal gas law. To use the ideal gas law, you may have to use the standard temperature and pressure in some cases. Okay, so you should know those values. Usually I give them to you, but they're pretty straightforward. Pressure is 1 atmosphere and so on. And then finally, in the application of gas laws, we learned about 2 applications. One was the density, and one was about calculating the molar mass of an unknown gas.